Hi, welcome to this session about Behind the Burst compiler, and thank you for joining. My name is Alexandre in French. I'm from France. I was told that I would have to start with this anecdote that you will not complain about all the English mistake that I'm going to make. I remember that 20 years ago I came to the US, and the first time I went to the McDonald's in the morning, and I order a breakfast meal, and I think that I said yes to all the questions he asked, and I end up with just a cup of coffee. So I would like to that it will be a little bit smoother for me today. So when I was a teenager, I was programming in, I was loving to program in assembly languages, and to use the tiny RAM and CPU that we had at that time, and to push the limits of what we could get from this CPU and RAM. And it went a bit more serious later with developing business applications and Java, even Java. And around 10 years ago, I started to use C# and the .NET ecosystem. It was actually almost all the combined productivity and performance that I was looking for. But I worked across the recent years to improve the performance and to abuse IL tricks and PNVOC optimization. But I knew that it was not enough. So when I was contacted by Unity 2 years ago to work on a compiler technology that could unlock this, and that Unity was willing to even embrace C# more, I was really happy to work on this. And here we are with Burst. So in this talk, I would like to you to get more insights about what's the magic behind the Burst compiler. I would like you to forget about the magic and understand what's behind. So you will be able to better understand it, leverage it. So in the first part, I would like to go through the basic original reasons of the project. And then we will see how Burst is working, how is it being used, developed, tested, how it is integrated in the JIT, in the editor, and how the JIT and the AOT is working. And then we'll talk more about optimization, what you can expect and what you should be aware of to better leverage Burst and optimize your code. And in the final part, I will just give you a glimpse about what you are working to work in the future. So let's start. Why Burst? Obviously, it's all about performance, right? So it's for games, but for simulations, for AI, for even real-time performance. And there are two aspects of it. First one is obviously codegen. The more your codegen is optimized, the more your program is supposed to run quickly. And we know, for example, that Mono is very slow compared to C++. And this applies also to some extent to IL2CPP and to .NET Core CLR. And one of the reasons is that they are general-purpose compiler, and they can take some shortcuts that a more optimized native compiler could take. It has also an impact on the memory access. The codegen needs to be friendly with your data-oriented design and your data-oriented code. And a poor codegen with a good DoD layout of your data is not going to give you the best performance. And it's not that you can do DoD to DA with C#. That's the contrary. For example, compared to Java, where in C# they got this right. You have value types that you can use, and the codegen is working very well. But in the case with Burst, this codegen is going to be more efficient. And it's also related to GC allocations. So in general, the GC is actually not the problem in your program. The problem are the inappropriate allocations that you are doing, the allocation that we could avoid, the allocation that we could manage differently. There is another aspect for Burst is that we would like to push for deterministic results, for floating point operations. So it's not yet part of Burst. I hope that we'll get something by the beginning of next year. But that's a really important topic for ECS. It's also about the language. We still want to work in C#. We also want to get the best performance we can. And C# gives us the fast development iteration that we are all looking for. And we want Burst also to deliver the same experience with the JIT. And so having Burst also delivered as a package, as it is today, is part also of this work of improving the development iteration time. So we can deliver Burst package more quickly to fix bugs more quickly. So how Burst is working? I would like to go through, start with just a timeline about the project, because maybe you're not aware about how did it start. So we started by a compiler prototype by early last year. And towards the Unite Amsterdam and Austin Unite, we did Burst were used for some compiler prototypes. No, Burst was used, but Burst was a compiler prototype. And then in September last year, we learned from this prototype and we built Burst from this. So then we released the first preview of Burst in GDC this year, integrated with ECS and with the JIT and the editor integration with the Burst inspector. And since then, we have been releasing more than 40 releases, I think, of Burst since its launch. And we released the preview of AOT compilation mode in July. And all of this is, of course, part of this performance by default equation that we want to challenge. So the compiler is composed of different parts, and it's a very standard way of developing a compiler. And actually, Burst is not really a compiler. It's more a transpiler, but I will get back to this later. And Burst has a front end that is responsible to translate the IL to some. So IL, it's called intermediate language for those that don't know what it is. It's the microcode that is used in the .NET assemblies that are compiled by the Unity engine, the Unity editor. And so both the JIT and the AOT of Burst are using the same front end, but they are just interacting differently with it. And we have inside Burst a backend that is responsible to interact with a Burst LLVM, which itself is going to interact with LLVM. And the backend abstraction that we have is acting just as a Burst IR, so an intermediate representation of between the IL and the LLVM representation that we have. And so we have tests for both the front end and the back end, and there is a special case in the way we optimize the math library, for example, that I will explain later. And of course, we are trying to take advantage of the context of Unity with the job system and so on. And today it's working on the three major editor platforms, 2 consoles, and the 2 mobile platforms. So one question you could have is why working from IL? For example, we could use Roslyn, that's the C# compiler, and we could translate directly from C#. But using IL is a well-proven technology, and it's actually very close to the representation of the IR in LLVM. And the way we can access it is well-proven. For example, we can use Cecil. That's the same technology that is used actually by IL2CPP. And so we are we are working from this side because it's much easier, and we don't need the source code, for example. Typically, that's nice. And we are working on a subset of a language, and that's one of the important aspects of Burst, is that we are mostly removing the usage of manage objects. And for example, for arrays, you would need to use native array instead of a managed array. And the native array is just a lightweight struct that is holding a pointer to an unmanaged buffer memory, and it has a count, a length. and that's a way we are accessing, for example, native arrays of data, for example, in burst. And for exception, we are actually supporting very basic form of exception where you still can throw exception, but it's going to end up into the editor directly. And so there is no stack frame, or you can't try catch exceptions. But otherwise, we support all the primitive types, the struct, the pointers, the control flows, except the try-finally for each that we don't yet support. And we call this subset HPC sharp, so it means high performance C sharp. We could have called it data-oriented C sharp, actually. But it would have been doc sharp, and then people maybe would have made fun about DeLorean C sharp, so I don't know. So it's not all about your code that we are going to translate to this subset. And we would like you to feel confident that you could maybe translate maybe 20% of your code that is going to cover 80% of the time that your game is spending. So that's an important aspect of it. So another question you could have is why not using IL2CPP? And the reason is that IL2CPP was originally designed for supporting the iOS platform because the JIT was not supported there. And it was primarily not really designed for performance. It was designed to support the full .NET ecosystem. So, but they are working on it. So I'm sure that the team of Jonathan Chambers and all the people working on the project will be able to improve the performances. But it's still a general purpose compiler, so it still has to handle the managed objects and the throws exceptions and so on. And for burst, we were able to experiment optimization that very quickly that would have been very difficult to do with IL2CPP typically. So, for example, we'll see later the way we are handling mathematical functions. That's very different from the way regular .NET ecosystem is working, the JIT or even IL2CPP. And if we want to experiment with LLVM customization, it would work as well. That would be more complicated for IL2CPP because they would have to fork LLVM to fork CLang, the compiler, the C++ compiler, ship it with Unity, with a Unity editor, so that would be more complex. But we could share some implementation in the future. So it's not like we are duplicating all the work, and the work is not so large, actually. But actually, Burst is already using a part of IL2CPP, and that's the linker that we're using. Another question you could have is why LLVM? And LLVM is a fantastic compiler library that has been developed for years. It stands for low-level virtual machine, but they dropped this acronym because it was not longer relevant to its usage today. Because today it's used by CLang and by languages like Rust. It's very extensible, very easy to use. You can extend with new optimization without even forking it. The code base is really clean, lots of comments, I like that. And there is a good debugging experience and a huge community. So if you have a question, sometimes they didn't respond to me, but that's fair, that's fair. So, an example, C#. We are going to add two numbers. I don't think it's very useful for a game in this case, but you can see on the left and right, blue and green. Yeah, maybe it's not good for, okay. And the plus sign. And in IL, it's like this. IL, it's a stack-based instruction set. So when you load an argument here, the left argument, and you load it on the stack. So here, after here, you have two arguments. And then there is this little add instruction by itself that is going to pop the two arguments that are on the stack and push the result of the addition. And then we are going to store it in a variable. There is lots of code here for adding these two numbers because it's a debug build, I think, when I did it. And in LLVM, it's very similar. You get the left and right argument and the operational here. So, but it's register-based, and it's regular instructions. So you have the add instruction, the argument left and right, and the result. And that's what LLVM is producing. That's an optimized version, actually. Usually, if you would have to program this directly in assembly language, you would have to use, some move instruction and the add instruction, but they are already optimizing a little bit the usage of the simple instruction by using a single one instruction in assembly. So even for the simple case, that's already optimized. I would like to go through the life of a job in burst, because that's your main entry point when you are going to use burst in Unity. So the first thing is that you usually declare your job that inherits from one of the iJob interface, and you have to specify the burst compile attribute. You can put your arguments, your input and output native array that are going to be used by the job, and then you implement your method, and you are going to schedule it. And this schedule is not going to run directly your code, right? Instead, the schedule method is going to pass a pointer to a wrapper here that is going to run your job. And in the case of iJob, the wrapper, it's an internal code that you don't see. But the wrapper is just going to call directly your method. We have other kind of jobs that could run differently your job. So maybe you could pass an index to your job as a parameter. That's the case for iJob parallel, for example. There is also something that we'll talk about just after. So an interface of the job system is inheriting as an attribute that is called job producer type. And it's a link between the job and this internal wrapper. So that's the static link, and that's the link that is used by the AOT compiler. But that's not the link that is used by the JIT, because the link that is used by the JIT is when you run explicitly on demand your code and you schedule a job that we are going to detect which job is it and which wrapper is it. So here you schedule a job, and this native pointer to the wrapper is going to the job system that is in C++, and that's in the C++ runtime in Unity. And the job system is going to communicate to burst to ask, compile this method for this job. And in the case of the editor, we are going to query to a JIT compiler that is embedded in the app domain in the editor that is persistent. And this app domain is going to, and this JIT compiler is going to produce the method asynchronously. And it will call back the job system with the method once it's compiled. And if there is any errors, it will print the errors in the logs. In the player mode, the burst C++ runtime will try to load here a share library. And this share library was generated at build time. When you build up your player, it's going to call the AOT burst compiler, ahead of time compiler, and it's going to generate this DLL that will be shipped as part of your player. And so we are working with two compilation modes. The JIT compilation, and it's determined by the job schedule method. So when you push a job, it's going to compile the method that you are actually running. And for AOT, we need to detect all the jobs that are going to be compiled. And we cannot run your code, so we need to detect it through this job producer type that I explained. And it's typically used in the burst editor, inspector. So on the left, you have jobs, a list of jobs, and this list of jobs has some elements that are white and some in the list that are gray. And the ones that are gray out are the ones don't have the burst compile attribute. And on the right side, oh, it's difficult for me now, there is the assembly view, the IL view, the IR view, and the analysis. We just added a few weeks ago a beginning of debugging, or at least where am I in this code, by pointing back to the C# code. So it's the yellow lines that you can have. So in the future, we want this inspector to be the optimization companion tool that will help you to optimize your code. So spot user code vs wrapper code, view side-by-side, C# and assembly code, view optimization diagnostic directly with your code, and get optimization guidance, for example. So why my loop is not auto-vectorizing and stuff like that. So we would like this to be really the companion tool where you will get insights about how you can improve your code. And maybe we will bring even like assembly instruction info for you to be able to read assembly code if you want. Let's talk about the testing infrastructure. So usually tests are paramount in any applications, right? But for a compiler, it should be really paramount, because if you make a mistake, you generate invalid code, it's going to impact not only you, but all the users of the compiler. So it's super critical. And compiler bugs exist, and they are a pain to isolate. For example, Coursera and the JIT, they have compiler quite regularly, even LLVM and MSVC. So it's quite difficult. So ideally, we would like to have 0 bug introduced by burst. And if we have something that we are not handling correctly, we would prefer to generate the compiler exception than to generate invalid code. But it hasn't been the case, so we need to be very careful. So we are developing lots of tests, but not enough. And I hope that we will bring more tests. But burst is closer to a transpiler, as I said earlier. So the problem is much easier to handle, because it's just to check the correctness of the IL transformation, the transformation of IL to LLVM. So it's not like the full stuff going to check if we use the right machine instruction for this architecture, CPU, and so on. And how we develop our test is very simple. We have a bunch of small, isolated C# code. It's a simple and unique test, but it's a little bit customized, so that instead of running some asserts inside your code, what we do is that we compile our method in C# with a JIT, and we run it with a JIT, the normal JIT, and then we compile it with burst. We run it, and we compare the results. And we can send variation permutations to the arguments, and we have 1,300 tests like this, and with a permutation it goes up to 30,000 or 40,000, something like this. And we are tracking regressions also by using assembly gold images. So as soon as we have validated some tests, we generate on the disk some assembly that are freezing the state of what we are expecting for the output, and then we are tracking this on every build, on every commit when we run the test. And there is a little bit of course, of magic to handle the floating point operation between Mono, .NET Core CLI, and Burst, because they don't give the same results, actually. So, optimization with Burst. There are 3 different aspects of the optimization that I would like to talk today. The first one is to talk about LLVM and compare it to Mono and .NET JIT, so that you will get a little bit more insights about what kind of optimization we are talking about. The second aspect is the optimization that we are able to bring through the Unity.Mathematics package for the mathematics types that we are using. The last part is about non-aliasing memory and how to take advantage of it for memory access and DoD, and that's related to how ECS is working and so on. Let's start with LLVM. So when you are talking about optimization in Burst, Burst is really the tip of the iceberg, and we are sitting on the shoulder of a giant, that is LLVM. And if you look on the side, you will see that the burst plays a tiny role in the full optimization process. For burst, it's mainly a matter of translating from IL to IR, but for LLVM, it's going to be a lot more complicated because they have to optimize the code to do constant propagation, inline the function, and so on. And then after translate the code to machine code, to register allocation, and that's lots of code and not really easy to write. So the box in blue are the part in a compiler where that are quite standard and that you will find typically in the same .NET JIT, for example. They have similar part, actually. But in LLVM, these parts are more optimized or are bringing more optimizations. So if you look at the optimization with LLVM, and I will take just the example of the IR transforms. That's what we have in LLVM today, all the optimization that we have. And that's one step among all the other steps that we have. So it's going to do, of course, expression constant, functions are inlined, loop could be unrolled, loops that could be auto-vectorized will be auto-vectorized, and so on. But there are lots of small optimizations. And that's around, maybe this part only in LLVM is around 130,000 lines of code. And the analysis just before that is very important, that is linked to the IR transform is 40K lines of code. Compared to burst, it's, we have only like maybe 20 or 25K lines of code of C# plus C++. So it's very small compared to all this setup. Let's look at the optimization that we talked about earlier, adding two numbers. So ReaJIT and burst are going to generate the same kind of code. Mono, for it's strange, it's generating some weird code, and it's quite unexpected. The arguments are passed on the stack, and there is a weird duplication of a load here. So yeah, even for this simple example, things are not as obvious as it could be. Like, it should be the same code in the end. The code is very small, but in practice, it does not happen. But this particular example would not really happen because most of the time, this function is going to be inlined by the call, at the call site, so you won't get this kind of code in Mono. But still, the way they are parsing arguments and so on are still here. Let's look at another example, BinarySearch. Okay, that's a very, very simple function. ReaJIT actually is 10% faster than burst, sorry. Mono is slower by 15%. So how ReaJIT can be faster? So the code gen is actually exactly the same. So I look at the code gen, and it's exactly the same. ReaJIT and Mono burst are generating the same code with the same number of registers used and so on. But actually here, that's the pinvoke, the DLL import, the fact that we are transitioning from C# to native code, and it has a cost. And this cost usually is about 10% compared to a blank code where you don't do anything in your code. And in the case of a binary search, for example, most of the time it's a binary search, so it's log n, so you are maybe like, if you have even like 10,000 elements in your code, you are going to have like 9, 10 loops, so it's not going to change much the performance. So that's why there is a little difference, and the cost of the interop is quite heavy, actually. So it's a micro benchmark, and the difference is marginal. And opportunities for optimization are very minimal, actually, because if you have a good, even like a simple register allocator in a compiler, there are not so many variables that are in this code, so it will be easy for a basic compiler to optimize it. But still, you are already getting a little bit of performance difference with, for example, with Mono. Let's look at Mandelbrot. That's another kind of micro benchmark. So ReaJIT is now 10% slower than burst, and Mono is almost 2 times slower than burst. And what's often important in a compiler is to optimize the most inner loop. And in the case of Mandelbrot, that's the loop that is here. And that's the loop that is going to iterate on the elements and going to pick up the values that has a certain limit. And this loop is going to run for each pixels in the Mandelbrot set. And so this loop is optimized differently by burst, by real-JIT, and by mono. And we can have a look here. On the side, you have mono. The code looks not good at all. We have like, I think, 3 registers out of the 16 registers that we have for floating point operation that are actually used. So there are what we call lots of variable spilling on the stack. So it's transitioning, moving back value from register to the stack and stack to the register. So it's mostly the sign of a weaker register allocator. That's one of the box that I highlighted at the beginning of the optimization. And for real-JIT, actually, that's much better. The registers are fully used, maybe a little bit too much, because I think that I counted there is like maybe 15 registers used. And it's going to be maybe a risk of register pressure at some point, but we don't see it here because it's all fine. We have enough registers. And there are like still 2 loads of constant. In the loop, there is a multiply by 2 and a comparison with a 4.0, a floating point value. But in burst, so thanks to LLVM, we are seeing almost something that could be written by hand in assembly language. So the register usage is optimal and very low. Constants are completely hoisted from the loop, and it has even detected one iteration that it could perform outside the loop, actually. So it's pretty clever. So we have seen that the .NET real-JIT for a compiler that is not used by Unity today, maybe one day, and can be actually very competitive on this kind of code, while the mono-JIT is still starting to be less efficient. But now let's pick one optimization. So it's called unswitched loop that is typically not performed by a JIT, a regular JIT, a standard JIT, a fast JIT, like a real-JIT or mono. So on the left, we have a loop which has a condition on the variable check that is actually an invariant, so it's not going to change within your loop. It's just a parameter that you pass to your function, and the loop is checking this value. And that's the kind of code I'm pretty sure you have already done. And usually we should maybe, depending on the cases, but we should write this kind of version where we duplicate the loop, we hoist the comparison of the invariant code into outside the loop, and we duplicate the loops because it has a cost to check this inside the loop and so on. So typically, the LLVM is able to perform this optimization for you automatically, so you don't need to do it. And so here we start to have a different performance ratio between burst and real-JIT, and it's becoming even more staggering with mono, 13 times, I think. So on the left, you have real-JIT content that is well optimized, no variable spilling at all. The code looks good, but the check inside the loop is still hurting the performance of the code. So it's a micro benchmark. Of course, it's not going to, not telling you that you are going to have you always have a 5 times speed up with burst. But on some case, you can have this kind of speed up. And on the right side, the difference is more important because the code is actually auto-vectorized. And the code doesn't do anything meaningful, but it's just counting the values that are different from 0 in the input array. So it's really not relevant. But so what we are seeing is that the difference with the auto-vectorization, and I will talk about this just after, is quite massive for your program. Another example about the kind of optimization that you can have with an LLVM that you will not have today, maybe later, with your real-JIT or mono. It's a function that is called, so let's write a function that is called CountBits. It's just a function in C# that is going to count the number of active bits that are in a single integer. And we are going to iterate on this on an array of integers, and we are going to count the bits. Maybe that's not something that you could use in a game, but maybe you could have usage. We don't know. And that's the code that is generated by Burst today. So what's happening here, and that's a lot. Huh? That's not what I wrote, actually. I don't know. So what's happening here is that we have, again, the vectorization of a loop that is in place. So a single loop is able to handle 16 values, 16 integers on one loop. And the count bit functions is actually even optimized to 1 when you are processing the remaining elements of your loop. For example, if your loop is not a multiple of 16, for example, we still need to process elements one by one, and we still have one instruction that is running on each remaining elements. And the compiler was able to detect that this whole code here is actually a single instruction for Intel x64. And that's the kind of optimization that you can get with LLVM. In .NET Core, for example, this could be mitigated by using system.numerics.vectors, and they are going to introduce some hardware intrinsics where you could do this almost, I think. The thing is, it's more laborious for you to do this kind of code because you need to explicitly use the instructions and you need to vectorize your code manually. But here, we get this almost for free. So the takeaways for the optimization with Burst and LLVM are that it's bringing major performance improvement, and LLVM with HP C# provides the best optimization for C# that you can have. The main JIT and AOT cannot compete with the LLVM compiler because they need to take into account the GC constraints. And we are, so the LLVM compilation time can be higher, much higher than a JIT or than mono. But it's probably less a weakness because we are optimizing for tight loops. So we are focusing on maybe 20% of your code that we would like to optimize, but it's not going to be all your code. Let's talk about the optimization with Unity.Mathematics. So Unity.Mathematics provide basic primitive types, and they are mapped directly to SIMD registers for your hardware, so for Intel and ARM4. And so we are internally storing these types in two ways. One that is used when you compute your data on the stack in a local program. We will use SIMD register, but as soon as you transfer them to memory, we will use different kind of representation. And so this is something that could hurt a little bit the performance, but it's a structural difference. Because in C# the float 4 is declared as 4 floats, and it's aligned on 4 bytes, and a SIMD register is different. It's aligned on 16 bytes, and it's 16 bytes long, typically. So we cannot use the same representation in memory for these types. So that's why sometimes you could have optimization that could not work well with some types. And typically, it's sometimes better to use float 4 info that are the size of the hardware register than to use float 3 and so on. So that's the types. And for the mathematics functions that we provide, we have 3 kind of way of translating it. The first one is we translate directly from C# to IL. And for example, there is mat.smoothStep. This function is just multiplying elements and so on. So we just translate it directly to LLVM. Another case is where we have an LLVM intrinsic in LLVM. So we can translate the burst intrinsic into LLVM intrinsic directly. And the last case is for the more complex functions where, for example, typically cos, sin, and so on, where we need quite lots of code. Cosinus is quite difficult, actually, to compute on an hardware that doesn't have CPU instructions. So we are using the Sleeve library. It's an open source project, and it provides a SIMD library that is very efficient on many platforms. And we use this, so Sleeve is compiled with in IR, to IR, so the LLVM IR. And in Burst, we are injecting this IR directly into the Burst intrinsic function that is just a declaration at the time. And then LLVM will be able to optimize this function as part of your code, so constant propagation will work, and optimizations of all kinds will work. And that's similar to what you would have with link time optimization. But we do this at compilation time, actually. And there is one key feature of Burst mathematical function is that you can compile job with a specific precision and some specific relaxation mode. So you can say, oh, I don't care about the order of the mathematical operation. I don't care about the correctness. And if you configure this in your job, it's going to be more optimized. And this applies transitively to your code. So if you set up this on your this Burst compile attribute with this accuracy support, you do it on your job, it's going to do it on your all mathematical functions that are used within your jobs. And that's one of the cool things that you can have, is you could have like 2 jobs sharing the same kind of code, but one job would run, for example, for closer camera elements and would be very optimized, but with high precision, and you would like to run this kind of code with for far distance elements with lower precision. And that's the kind of thing that you can do with Burst, and that's something that would be very difficult, or not very difficult, but a little bit more painful to do in C++, because you would have to use preprocessors, you have a makefile around to perform the compilation of these variations and so on. So note that for AOT, this is not working, actually. So that's something that we'll have to fix. It's working in JIT, but not in AOT, actually. But we'll fix it, hopefully by the end of the year, for Christmas. So optimization memory, and I have only 3 minutes left, so it's going to be quick. So the memory aliasing problem is when you have a memory location that is going to be accessed through different variables. And when a compiler usually assumes that aliasing is happening in your code. So the compiler cannot optimize your code as it could. So when, for example, we take this example of just a simple function that is moving a variable A to B and to C, you will see that if you don't tell the compiler that A could not alias with B and C, it's going to be to reload A to a register here when transferring the value to C. Because maybe when you wrote A to B, maybe it was aliased a little bit with A and directly, and you would have a different value for A. So when you inform the compiler that A doesn't alias, it loads the value just once. So it's a big deal, it's just one instruction saved, right? So it's not like it's going to increase the FPS of your game. But for arrays, it's become more critical, because the optimization of the loop is going to be more dramatic if you can have memory aliasing configured correctly. And the loop, the compiler will be able to optimize this loop more efficiently. And this example, for example, we have we are copying values from one array to another arrays, and we are doubling the values. And you could vectorize this code by hand, or you could let the compiler to auto-vectorize this code. And if we look at the way it's working, on the top, it's when it's vectorized, and we don't have any aliasing, and on the bottom, it's when it's we have an aliasing, actually, and it's vectorized. And the output, for example, will be completely different. So you need to be very careful with aliasing memory. And what's the code is generated, it's like this. It's for, when it's not auto-vectorized, it's very Scala code. But when it's auto-vectorized, it's going through 32 elements per loop in a single loop, and then it's going to try to handle the remaining elements. So the performance of the auto-vectorizing can be dramatic for your game, for your application. And, but you need to check the generated code, or at least you need to benchmark your code to make sure that you are not missing a performance decrease, because sometimes LLVM is not able to detect some patterns in your code, and maybe you will switch back from vectorized code to non-vectorized code, and that could have quite a significant impact on your code. So there's quite some text here, but we have, I'm not going to run on all of this, but we have a no-alias analysis that is going also to improve the detection of the no-alias for your code so that it will be more compatible. And I will just finish with 2 slides. Yes. So future is 1.0 release for mid-June next year, hopefully, with a real 1.0 and not a preview. We hope to improve the compiler quality and having more tests and so on. And we will work on DLL import. That's already there. Access to managed arrays of read-only data, deterministic floating point, a little bit of debugging experience. We would like to improve the editor, inspector, and more performance for ECS, so automatic SOA and so on. And thank you.